Let me share my screen.
Yes.
Um, Today I switched to another device because of that writing issue. So today primarily we will be covering this thing. If you remember in the last class we covered till the quantum teleportation, where we have seen that how we can reconstruct a particular quantum state, where though no quantum information will be shared between the sender and receiver, we will be just sending a few classical messages through some classical channel, maybe telephonic channel or something. And after that, a particular arbitrary quantum state about which the sender will also not be having much information about will automatically be somehow through some minimum logic, quantum logic will be generated, not cloned, rather generated by the receiver. That was the idea of the quantum teleportation. And before that, we also covered the introduction to classical cryptography, where and also we have seen that RSA, how the asymmetric and the symmetric key cryptography techniques work. And then we have talked about the quantum threats and which algorithm is causing the threat and all, and what is the threat potential of the classical on the classical algorithms by quantum. And then we introduced that we actually needed two solutions. First one is the quantum safe solution, which was classical, but still it has the potential as of now to beat the quantum computing attacks, and which this domain is also known as the post quantum cryptography or PQC. And then we left at that point where we needed some of the solely quantum enabled and quantum secure cryptographic framework, for which we opted for the full-fledged quantum solution, which was or that particular field, it is called as a quantum cryptography. And then we have seen that because here we are incorporating or employing everything quantum, where a quantum bit or say photon will be transferred through some quantum channel, and quantum bit or photon can be either a mixed state or a pure state that will be transferred. So that brings us into exploring the how we can transfer it, and there we talked about the quantum teleportation. So that was the basic flow that we covered. So today we will be covering exactly from the reverse point whatever we have discussed, where now we will see another technique, because in a communication channel there might be a situation where a quantum state also needs to be somehow interpreted by some sender or receiver in order to get back or say decode some of the classical information. So what was the inverse technique of quantum teleportation, for which we were talking about the super dense coding. So today we will start with the super dense coding, where we will see that how the quantum to classical interpretation works. Then we will talk little about the entangled Bell state so that we can get into the entanglement as well as the fundamental of the quantum cryptography, where the evolution of quantum cryptography, like what was the initial thought behind the QKT protocol and all. We will be talking about a little of that. Then we will end our session with describing in detail at least the BB84 protocol, which is the most famous QKT protocol. But before discussing all these things, I also made one commitment to lecture back. That is, I will be covering so 10 to 15 minutes at least. Actually, I committed that in lecture 6 only I will be covering, but because of some technical issue, I couldn't cover. So that was a part of the Grovers that was pending. So for which, first I'll be taking 10 to 15 minutes of that. But please put these slides once you download it into the quantum algorithm part just after Grover. Whatever we covered at Grover, after that you just put on these slides. Then we will start with the super dense coding. That is somehow what I have planned for today's class. Now, let me continue. So I will not put much point here, just to tell you that we talked about that Grover iteration number is order of root over of n. And we believe that one iteration of Grover, one say Grover iteration, can make an angle between your entangled, superposed state and the state W, the angle between S and W, that was your 2 theta. Okay. And what was theta and all? Just see, look into the geometric interpretation. You will see that what angle the superposed state is making with the perpendicular component of W. W is a mark state. So with that information, we will be exploring a little more of that. Okay. So just a minute. Yeah. So remembering the angle between, so the angle between, so in any easy words, that means after one iteration, the angle is increased by 2 theta. This is the increment part, okay? Not the exact angle, but the increment part. And what we want to just reduce it through several iterations. Okay, so this is the gap, right? So angle is increased by 2 theta. And how many iterations we need? Say m iterations. That was our assumptions, and we have seen m is nothing but an order of root n. So after m number of iterations, the angle between S and W will be what? It will be basically between your S and W will be, that is theta bar, which was initially pi by 2 minus theta for one such loop. So for m number of iterations, it will be pi by 2 minus, this will be theta into, or in easy words, it will be theta plus 2m theta within a bracket. One iteration will increase it by 2 theta, so 2m m iteration will increase it by 2 into m into theta. So now, which can also be alternatively written as pi by 2 minus 2m plus 1 into theta. And amplitude is amplitude of W in S. If you remember, W is nothing but a subset of S. It belongs to S. That is the reason for which we want to do the quantum amplitude amplification of W. So this was sine of 2m plus 1 into theta, which is equals to sine, let me put the value here, exact value was pi by 4 into root n. Okay, the value of m was this, plus 1. So this entire thing into theta, something like that. So it will be pi by 2, right? So that means it will be is equals to sine pi by 2 plus 1 by root n. 2 into pi by 4 is pi by 2. So this can also be written as sine pi minus pi by 2 minus 1 by root n. Because it's pi minus, just I'm taking minus as common. And now if you know the quadrants, it's all sine, tan, and cos or cosine. So this is pi. So that means pi minus anything will be plus sine theta. Sine pi minus theta is nothing but plus sine theta. So that means it will be nothing but sine pi by 2 minus 1 by root n. Now we know sine pi by 2 minus theta is nothing but cos theta. Now what is the series of cos? Cos x is nothing but 1 minus x square by 2 factorial plus x to the power 4 by 4 factorial minus x to the power 6 by 6 factorial and so on up to infinity. Therefore, cos 1 by root n will be nothing but 1 minus 1 by 2 factorial into 1 by root n whole square plus likewise. So again, ignoring the higher order terms, it will be something like 1 minus 1 by 2 into 1 by n. That is 1 minus 1 by 2n. So what we have established here is cos 1 by root n was the formula of this thing. So this leads to our derivation where the sine 2m plus 1 into theta is nothing but 1 minus 1 by 2n. Now, what is theta and what is n? You know, n is the number of steps or the number of inputs. Therefore, this is the relationship between the n and theta. So, this establishes the mapping between my theta and number of steps n. Okay. That was one of the proofs or the interpretation of theta versus n. That relationship we tried to map. There is another form of interpretation of Grover altogether, which is a matrix form. Right? So this can be represented by a matrix. This is the row and this is the column. And how we can construct the matrix is by minus 1 plus 2 by n. If I is equals to j, that is the diagonal elements. And it will be 2 by root n only if I is not equal to j. And of course, you can identify that it's a some square matrix. Right? Something like that it will be. So that means, and what is your D? Your D will be minus I is the identity matrix, plus 2j by n. Okay. What is J? J is an n cross n matrix where each element is 1. Exactly 1. And this J by n is known as projection operator. What is the meaning of that? That is J by n whole square will be nothing but J by n. Okay. So in that case, on this condition, say I want to put D, this particular matrix capital D on a column vector of n states, A1, A2, likewise AN. So this is nothing but doing this. A1, A2, twice AN. If you compute it with respect to a particular n, just take some examples. Say n equals, you can do it yourself, n equal to 4, then of course j will be 1, 1, 1, 1, 1, 1, 1, 1, likewise. Okay. Likewise, if you do, and of course your I will be this thing, 0, 0, 0, 1, 0, 0. Just by an example, you will be understanding it better. That's what I'm trying to say. And n will be, of course, 4. So if you just put the values with respect to, say, A1, A2, A3, A4, that is, I have 4 entries, then it will look something like that. And if you generalize it, it will look something like 2 into A bar, and A bar is the mean amplitude. 2A bar minus A1, this A1. 2A bar minus A2. Likewise, it will go on. It will be 2A bar minus AN. And just take an example and just do this. Like 2 by 4, that is half into 1, 1, 1, 1. So all will be half. And this is a minus 1. Like all the minus ones will be here if I do minus I. Then you add them. So after all these things, it will be exactly the same. And the column vector will be as it is. So sorry, very sorry. You will be just multiplying it. So there will be nothing like that. Yes. So after incorporating, it will be something like that. So say my n is equals to 4. Let me show you. That means j by n will be nothing but j by 4. So equals to j by 4 times So that will be j by 4 into a1, a2, a3, a4. And j is what you know. So just 1 by 4 will be taken there. So it will be, that means j is one, nothing but 1, 1, 1, 1, all ones. And then you take 1 by 4 with all of them. So it will be a1 by 4. Right? Now if you do this, we'll be getting this thing. Say a bar or a bar, any way you can write it. Right? Or sorry, let me just write a1 now, or simple a, because right now it's same thing only. And what is a? A is nothing but, or a bar is nothing but a1 plus a2 plus a3 plus a4 divided by 4. The mean. So it will be exactly same. Then multiply it and check it. What will be the value? Okay. Like a1 plus, it will be simply a1 plus a2 plus a3 by, plus a4 by 4, which is a dash. Likewise, this one will also be a1 plus a2 plus a3 plus a4 by 4. Likewise, it will be for all the values, it will be a1. So that means now if you do minus I plus 2j plus by 4, we'll be getting exactly the same thing. 2a bar minus a1 which was the same value that we were trying to put here. So in generic terms, that means if D is applied on any arbitrary state psi, where here we have taken a1, a2, a3, a4, it will be the sigma x to a bar minus this amplitude, respective amplitude of x, that is ax, and times get x. And with respect to this diffusion operator, if I want to write this thing for Grover operator, it will be something like WRW. What is R? R is the selective phase rotation. Phase rotation means that one minus one thing. And W is nothing but the Hadamard, or say Walsh-Hadamard transform. It's nothing but the Hadamard gate. So this is another formula or interpretation of Grover. So in these terms, that means your circuit of Grover will look something like this, where all of them will actually pass through, everyone will pass through Hadamard operations. So I'm just writing it down in this way. Tensor product n, say I have these n qubits here, and one will be my Y, or the target register, which will be, of course, first not applied or not get on it. So it will be 1 from 0, it will be 1, then I will be applying an Hadamard. So skipping all of them, I'm directly writing. So Hadamard on 1 will give me this state, and all of them together I'll be feeding to the Grover oracle. And this particular thing, then the output will again go to this D operator. Then this output will again go to the UF, and likewise it will go on. And here also it will be a UF, the unitary. And likewise these conversion will keep on happening. And after this, I will be simply measuring it. That is a measure here. And if I keep on doing this, this will give me how many times I have to do that. I have to repeat this for to repeat this for m within brackets root over of n iterations. Now you go on to the Grover, check it, so it will be exactly same. Okay. Now this was the part, and please include these slides here. This is just another interpretation, but the most strong interpretation was the geometric one, where we actually converts to the fact that one such iteration is going to take 2 theta. Then the second form gives us the interpretation where number of iterations we can actually put a limit of that we shouldn't be exceeding more than root over of n number of iterations. Then it will ultimately lose to lead to a less performance than what we can opt with exactly root over of n number of iterations. You can do one thing. You can actually try to put some values and check that exactly how many iterations you are getting. So you will see that after root over of n number of iteration for a particular value of n, you will not see either any advancement or you might see some degradation of the performance. So this is the optimal value that you should be picking up. Okay, so the next one was the super dense coding. As I said, that here we believe that from some classical information, we will Alice has to send some classical information through a classical channel, and the quantum state was prepared in case of teleportation. But here, why it's called a dense coding is because Alice here wants to send a classical information. So this is the output that we need. And she has to do this using a quantum state. That means a quantum state here is the input. So it is the inverse of the teleportation process. So here Alice will be sending one bit of quantum information, and from that particular bit, Bob has to extract 2 bits of extract 2 bits of this is will be classical information. Okay. And here, of course, just like teleportation, here also we need an entangled Bell state as the starting point to start working. So the thing is, and this is kind of a circuit. This is kind of a circuit. And this is the entangled Bell state. Where here also the idea is some maybe some sort of entanglement will be shared by Alice, and similarly a part of the qubit will be shared by Alice, and the remaining part will be shared by Bob. Okay, so that means Alice wants to send 2 bits of classical information, and she will be having some state. Now the generic idea is out of the Bell state that we talked about. So what are some pre-assumptions are there? We will start with the pre-assumptions, and the assumptions are, or say generic assumptions are, or idea are. So point number one, out of the Bell states, one will be with Alice, one with Bob. This is the first case. Second is Alice will be doing some part of or some sort of operation on her part of qubit. That means the qubit will be modified. So the result will be some modified qubit. Then the modified qubit will be sent to Bob through some, what kind of channel we need for that? A quantum channel. So remember here the qubit, that is a quantum state, is being transferred. Okay, not some classical one. Now Bob, on receiving the modified qubit from Alice, and or like now Bob has 2 sets of information. One is Bob on receiving the modified qubit from Alice. This is point number one that Bob has. Now, modified qubit from Alice. And second is what Bob originally has. Originally has will do certain measurements certain measurements on his part of qubit. Now see the effect of that Jurva movie that we were talking about. Since they both are sharing some sort of entangled qubits or a pair of qubits, so one will be shared by Alice, one will be shared by Bob. Now, depending on what classical information Alice wants to send, accordingly, Alice will be performing some operation on her part of qubit. But because her part of qubit and Bob's part of qubit are not on the same page, definitely they will differ. So Bob will only measure that difference. And based on the difference from his original state, because they are entangled, right? So the next, or say Bob's and Salman will also be affected to some extent. So maybe his hair is now clumsy. So in that case, Bob can understand that okay, initially what sort of actor I had, his hair was perfect. Now it is clumsy. So that means this hair transformation can happen only if there is certain change on the hair. For example, or say nose is like there is bleeding from nose. So likewise, depending on what I had and right now, what is the differential change that I am getting on my part of qubit, Bob is measuring the difference. And with that difference, Bob can infer that definitely that means Alice must be doing these particular information so that I am getting the reflection of the effect here in my set. So based on that, now he will be able to infer, right? That what two classical bits Alice would have wanted to send to Bob. So this is a generic idea. Now we'll see to the quantum circuit and how actually this is being interpreted. So you can understand that how important and how critical it can be for the quantum communication. So both teleportation and superdesk, they work hand in hand in order to implement the basic of quantum communication. So now schematics of the circuit will be something like say this. Let me draw the circuit, then I will be describing each part of it. So this is Alice's part, and post that there will be some C naught. You must be knowing what do I am trying to do with the header and the C naught. So this is a size state now. So this particular part is nothing but my entangled belt state generation. It's mandatory 0 0 plus 1 1 by whole 2 that thing. So this is the belt state generation step. Post that, it will actually go to some unitary. What do I mean by that? See whose line is this? Alice's. And who is doing the some modification on his part of, sorry, her part of entangled qubit? Alice. So this is the quantum oracle operation or some unitary operation done by Alice on her part of qubit only. So that is why I'm just putting a line and putting this as an input to the oracle for only Alice's part of qubit, not on Bob's part of qubit. So this is a unitary operation that Alice will be doing, which is some modification. And this will be sent to Bob through some quantum channel. So now what is the thing? Now it will be a reverse operation. And this Hadamard. This is Bob's way of interpreting that I'm going to get. So this is particularly this part is particularly sent through some quantum channel. And this entire thing basically a part of Bell state measurement. That is the difference only, right? So exactly this is what we will be doing. So here it will be initially it is nothing but 0 and 0 was there. I'm hammered the first one. So it will be 0 plus 1 by root 2 product 0, which is nothing but 0 0 plus 1 0 by root 2. Then on C naught, it will be simply 0 0 plus 1 1 by root 2, right? So the entangled state that Alice and Bob share is this thing. Now say, Alice, what Alice might be wanting to share or can be, what are the possibilities that Alice wants to share? Alice either can want to share 0 0 or 0 1 or 1 0 or 1 1, right? So Alice can share or want to share either of 0 0 or 0 1 or 1 0 or 1 1 to Bob. And now it's Bob's task to interpret it. So now depending on what I told, depending on what Alice wants to send, Alice will be doing the operations on her part of qubit. So now say Alice wants to send simply 0 0. Then what Alice will do? Alice will do nothing. That means what is the status of the Bell state? 0 0 plus 1 1 by root 2. Because Alice has done nothing. So how Bob will measure it, we will look into that later. Say now Alice wants to send 0 1. Then Alice will do, what Alice will do is this thing, which is nothing but, that means a NOT gate, right? This is a NOT gate, this is an identity, which is nothing, just a simple NOT gate. So it will be 1 0. This 0 will be 1 and this 1 will be 0. No change. Say now Alice wants to send 1 0. Then Alice will be doing the operation I times y, the Pauli y gate. Why I'm incorporating I? I'm just telling you. Product I. Now let us see what will happen because it might be not so familiar operation. So y is nothing but sigma y or y, capital Y, it is nothing but this thing 0 minus I 0. Now if I put up I into sigma I or say I times capital Y, it will be I will be multiplied. So it's I into 0 minus I and 0. Just multiplied. So it will be 0. This will be I square, which is nothing but minus 1. This will be minus I square, which is plus 1. And this is 0. So this is the matrix. Right? Now, say, let us see what will be effect of this thing on that particular qubit state. How it can affect. That is the IY operator can affect ket 0 or ket 1. Why? Because here I want to do with the ket 0 and here I want to know that what will happen with ket 1. So for that I should individually calculate that. So on application of this IY on ket 0, it will be 0 1 minus 1 0. This is IY and this will be applied on ket 0, which is 1 0. You multiply it, so it's 0 into 1 plus 1 into 0, and it will be minus 1 into 1 plus 0 into 0. So it will be 0 and it will be minus 1. That means the result will be nothing but, so minus 0 1, and 0 1 is ket 1. So IY on ket 0 is making it minus 1. Similarly, IY on say ket 1, it will make it, ket 1 is 0 1. So just multiply it. So it will be 0 into 0 plus 1 into 1, that is 1, minus 1 into 0 plus 0 into 1, that is 0, which is ket 0. So that means this will be now what? So this will be, your 0 will be minus 1. So that is minus 1, 0. And this one will be simply 0. So plus 0, 1 by root over of 2. Okay. Clear mathematics. No such quantum thing here so far. And the next one is, if Alice wants to send, so fourth case is, case 4 is Alice wants to send 1, 1. So 1, 1 if Alice wants to send, she will be doing Z into I. We all know what Z is. Z is a phase gate. And Z does nothing if it is 0. And Z only changes the phase if it is 1. So that means initially it was 0, 0 plus 1, 1 by root 2. This was your initial state. So Alice, after Alice's modification, it will be 0, 0 will be 0, 0. And the 1, 1 will be minus 1, 1 by root. Okay. So now that means 4 different types of things can possible. Alice can either receive this, Bob can either receive this, or Bob can receive this, or Bob can receive this, or Bob can receive this particular, right? So now that means, now Bob has 4 different Bell states. So now Bob will be doing a C naught operator first. First a C naught operation. Okay. So the effect of, just you see here, there is a C naught operation. So that will be, that means effect of Bob C naught. Let us see. So what Bob can have? So if it is 0, 0, Alice wanted to send 0, 0, thus Alice must have sent this. And now on this, if you apply Bob C naught, it will be what? 0, 0 plus 1, 0. Because it is 1, so it will be flipped, divided by root 2. Right? Similarly, if it is 0, 1, then Alice must have sent this. And on Bob C naught, it will be what? No change, because here control is 0. Similarly, for remaining 2 cases, if it is 1, 0, then it is minus 1, 0 plus 0, 1 by root 2. Alice must have sent this. And this on C naught will be minus 1, 1 plus 0, 1 by root over of 2. And if it is 1, 1, then Alice must have sent this. And this on C naught will be 0, 0 minus 1, 0 by root over of 2. Okay. Okay. Now check in cases of 1 and 4. See here, in case of 1 and in case of 4, these are Bob's qubit. Okay. Bob's part. So in case of 1 and in case of 4, second qubit is 0. So now in cases of 1 and 4, second qubit is equals to 0. And in cases of 2 and 3, the second qubit or Bob's part of qubit will be actually 1. So, or alternatively, we can say if second qubit is 0, then what Alice must have sent? Either 00 or 11. 1. And if your second qubit is 1, that would mean Alice must have sent either 01 or 10. Right? Now, on that note, considering the second qubit is 0, go back, let me go back. Considering the second qubit is 0, I'm applying an Hadamard on the first qubit. Till this part I have done. See, no, Bob C note is over. Right? And why this is Bob C note? Because the target is the Bob's qubit. So Bob C note it will be. Okay. Where it is depending on the control from Alice's qubit. So now what will happen? Bob will consider that, okay, let me fix now my part of qubit, which is 0. Second qubit is 0. And let me only apply Hadamard on the first qubit. So considering second qubit as 0, and applying H on first qubit, it can be either this thing, either it could be this, definitely, or it is 0 minus 1 by root 2 times it was 0. Now, if I measure any of them, here it will be, this is Hadamard, and a Hadamard and measure, so it will be ultimately 0, 0, and here it will be 1, 0. So that is here it's a 0, 0, or here it's a 1, 0. So there should have been a combination of logic, right? Where the like the of the first and the second qubit. So a combination of logic of the therefore a combination of logic of first and second qubits will enable Bob to infer what exactly have been said. So now it will try to measure. Now say my second qubit and first qubit. I'm just writing in this order. So that can be either 0, 0 or 0, 1. Second qubit is 0. This thing I'm just writing together. Or it can be 1, 0. Or it can be 1, 1. And what logic it can be? So let me write here. So second and first. And this is the logic. And this is the interpretation. By whom? By Bob. So either it's 0, 0 or it's basically 0, 1 or it's a 1, 0 or it can be a 1 1. So that means what? It will be if 0 0, then if the second qubit is 0, that means either it is 0 0 1 1, just you check, or if the first qubit is 0, that means it can be 0 0 or 0 1. Similarly, second qubit is 0 means it can be either 0 0 or 1 1. Same logic. Here also the second qubit is 1 means here it can be either this. Second qubit is 1 means it is 0 1 1 0. It cannot be 0, otherwise it could actually be a part of this. So similarly here, if it is 0 0 0 1, then this one will be 1 0 or 1 1. Similarly here also it's 0 0 0 1, because here its first qubit is 0, so it can be 0 0 or 0 1. Similarly here it can be 1 0 1 1. Now just you check. So 0 0, either it can be 0 0 1 0 1 1, or it can be 0 0 0 1. Though it's or, don't take it like a set union or something, right? So either it can be this or this. But what is the common in both? That is 0 0. Similarly, what is common in both? 1 1. Similarly here 0 1 is common. That is irrespective of what was the first and the second qubit, blah blah blah. If the combination is this after measurement, then it has to be 0 1, because 0 1 is definitely there. So it can be either 0 1 or 1 0. And for this first qubit as 0, it can be either 0 0 or 1 1, 0 0 or 0 1. So 0 1 has to be common between both. And similarly here also it will be your 1 0. Now you see, you just had a classical, say, a Bale state, and you wanted to send all these four, say, cases, or say four two bit information to Bob, and how using a quantum channel and using a quantum state, which is a Bell state, you actually have transferred a particular classical information through a quantum channel. So that means quantum teleportation is something where we actually send some classical quantum state. We are sending, the channel is classical, and in quantum dense coding we are use sending classical state, which is nothing but classical bits, and the channel is quantum. These were fundamental building blocks of quantum communication. Let me pause here a little. If anyone has any question, you can ask. So, any question, anyone? Till this part, is there any question? All the comments are non-technical. Okay, I will wait for 1 more minute. If you have any question, you can ask. Last slide, definitely. This is the one. I'm fast. Okay, okay. Okay, I'll be slow. Yes, okay. Logic part of dense coding. I'll be explaining it again. Except the dense coding part, nothing else, right? The logic part. Yes. Yes. Okay. So, yeah, the logic is this thing. So we are considering two different kind of thing can be possible. First is the second qubit can be either 0 or the second qubit can be 1. Then you have to understand that why we are suddenly picking up the second qubit. If you just go back, that all the four cases, what Bob can get, see the circuit first. Unitary is done. That means after this thing, Alice can send any of the four modified qubit. That particular thing Alice can send. After that, what Bob is doing, Bob is just applying a C note. So this is what I am referring as Bob's C note. Okay. So that means after this, Bob will be doing C note. So this is what Alice might have sent. So if this was something Alice wanted to send, Alice must have not done anything on the bell state. So if Bob measure it, Bob does a C note on that. So it will be, this is control, this is target. So nothing will be here. And then this one is control and this one is target. So definitely target will be flipped and it will become 0. Now consider, this is Alice's part of qubit, this is Bob's part of qubit. This is or say first qubit and second qubit. And this is also Alice's part, which is first qubit. This is Bob's part, which is second qubit. Right now, it is not associated with Alice. That is why we are calling it only the first, second. We are naming it accordingly. So that means this particular thing will be 0 for the case where Alice must have sent 0, 0. So my second qubit is 0 for this particular case. First qubit is flipping, so I'm just considering the constant one here. Similarly, if you consider here, the second qubit is 1. Here also, the second qubit is 1. And here also, the second qubit is 0. So in case 1 and 4, in case 1 and 4, my second qubit is 0. And remaining cases 2 and 3, my second qubit is 1. So if second qubit is 0, Bob infers this thing in this way that Alice must have sent either 0, 0 or 1, 1. And if my second qubit is 1, that means Alice must have said either 0, 1 or 1, 0. Okay. Now considering the second qubit as 0, there will be an Hadamard gate on the first qubit. How we are getting that? Go back to this thing. See, there is a Hadamard on the, sorry, yeah. So Hadamard on the first qubit. And if I do that, what do I mean? There can be two different possibilities. That is, let me now go back. So that means either it could be this thing, ket0 plus ket1 by root 2, or it could be ket0 minus ket1 by root 2 in that particular state. Now, if you again apply an Hadamard on this thing, so this will become If you are having any difficulty in understanding how I am writing this, so this is exactly similar to writing this thing, and this one is exactly similar to writing -10 by root. I'm just writing it in this way so that I can easily show you that how after Hadamard you can yield a 0 for the first qubit, and second qubit is already 0. So that means either it can be 00 or it can be 10, nothing else. Okay. Now exact same logic you have to apply for the second qubit, considering sorry, on the case where it is the different one. So for this particular thing, now we have done like 00 and 10. Now say come back here. So your first qubit can be either 0, second qubit consideration, you got it. Now your first qubit, if it is 0, that means definitely it can be either this 00 and 01. First qubit is 0. And if your first qubit is 1, it can be either 10 or 11. Similarly, first qubit 0 means it can be 00 or 01. Because one of the qubits I already have fixed it. And if first qubit is 1, then it can be either 10 or 11. Now this is after measurement, this is after basic logical deduction. Now if you merge both of them, so what is the common between this particular part, like this part and this part? Two different interpretations are coming, and I have to combine them. Then I will be getting that, okay, so either I can wear a blue shirt and a red shoe, or I will be wearing a blue shirt and maybe some green dress. So if someone else asks you that what exactly my preference is, what is guaranteed interpretation that you can get, that definitely I will be wearing a blue shirt, because red dress or red shoe and green dress can vary in multiple cases, but this is something where it will not vary, right? So that is how we are interpreting the logic in this way, and which is common based on both different interpretations, and this is the output that we are getting. So it's just like a lever. We are or pivot. We are pivoting one and then checking that what now first can be either this, or first can be either this. If second is one, then first can be any one of these two. Match the both logics, then we'll be getting it. Okay. A few more slides, blank slides, and we're deleting it. So here is some, like in the PPT also I put it. You can check that. All the details are mentioned. Okay. So now we will enter into, so we have covered the Grover part and we also have covered the super dense coding. So what is left? We are left with the topics of quantum cryptography primarily. Okay. So, and I also have some thought, but I will be discussing once the entire discussion of this thing is over. So if time permits, I might talk about a part of the error correction as well, because of one was asking for that. So maybe not one or not all, but at least a glimpse of that we will be getting. You might get. No commitment if this is done. So entangled states are, you know that it's a making a local measurement on either of the first and the second qubit, where it will not be providing any information about how the system was prepared. So preparation, non-contextuality will always be there. That thing is for sure. And we can say that measurement of first qubit collapses the entangled qubit as well. This is a very basic essence of entanglement. So what entanglement is, in again, if I have to say, it is the kind of a behavior of two quantum particles, that the way one behaves, the other one, no matter how far they are with each other, will also behave the similar way. Now it's not the same, rather the similar. Depending on the nature of the correlation, it can be either positive correlation or anti or negative correlation, depending on their spin will be up or down. So that just like the relationship, either it can be proportional or it can be inversely proportional. But there has to be certain relationship. Okay. And Einstein first actually didn't agree with that, and he called it like a spooky action at a distance. It cannot be. Okay, but and he also like challenged this thing that nothing can be faster than light. So if something is very far or a very far distance than each other, then how it is practically realizable. So all these kind of things that were said whenever measurement comes into picture, you know that measurement is a classical thing. So it automatically collapses it. And there is definitely some error correction and decoherence thing for the photons will be there. So after this thing, he actually agreed that for with a particular small setup, this quantum phenomena of entanglement works exactly properly, though I'm not sending it. So it's a spooky action at a particular at some distance. That flavor he will be getting. But though we can say that even if they are separated by a space-like distance, that was some sort of commitment. That even if they are separated like a space-like distance, they will be entangled. Yeah, theoretically they will be, but you might not be having some interpretation of that because everything has to follow the classical relativity of light, at least in terms of measuring it or measuring the entanglement outcome. Okay, so Bell outlined this, the scientist Bell, who's like Bell states and all we are talking about. So Bell outlined three assumptions about the world, each with the corresponding mathematical statement. One is the realism, that objects have properties that they maintain whether they are observed or not. There is something is there in the universe, they are real, but maybe they are not observable, or there is no such apparatus with which we can properly observe it. Or maybe there is no requirement for which we are not observing it. But definitely they exist. Second is locality, that nothing can influence something far away such that a signal between them would need to travel faster than light. So it actually supports the relativity theory as well. Into 10 to the power meter per second, the speed of light. So locality principle has to be there. Third one is the freedom of choice, that physicists can make measurements freely and without any influence from hidden variable. What do I mean by that? See, all the quantum, whatever discussion so far we are doing, they are not 100% fail proof. Now, mathematics is fail proof, but physics may not be fail proof. Why? Because everything has certain effects of the environment, and that will definitely influence the measurement that we can make. So, this is measurement are of two types. One is the free set of measurement that we are doing. Whenever we are measuring, it may be meanwhile as well. Say we started the measurement, say for example, in the macroscopically, we have started the measurement at 10:01 a.m. and it will take maybe 30 seconds. So within that time period also, there will be minute such like intervals where its behavior might change. And how it will be changed depending on the environment. But we are just assuming for measurement that at least for that instance, the measurement interval, it will not change. And not only that, there can be some hidden variable effect as well, which might distort the outcome. But again, the thing is that because in nature it is often the case. But here we are exactly simulating that kind of behavior where nothing like that happens. Why? Because we are trying to compute something. We are not exactly using the quantum physics, we have translated the physics phenomena like superposition, like entanglement into a measurable computing, which is known as a quantum computing. And that is the definition of a quantum computer. But definitely here we are assuming that there is no such influence of hidden variable. And we can make some free measurements based on that. But again, the truth and the real underlying truth is nature does not follow these assumptions, which imply that quantum entanglement in real and subatomic world in truly or is truly as strange as it seems to be. So maybe there it can travel better more than faster than light, or maybe something like that. But classically measuring it is not possible. And we are not only telling that quantum entanglement exists. That's a realism. Definitely it exists. But what I want to do is I want to measure the entanglement, or I want to get the benefits of the entanglement. We want to use it for the security purpose. So just consider the example of the dense coding. What we are assuming that if this is 0, 0, the Bell state, so definitely that means Alice and Bob should be having the same set of Bell states available, or same part of the Bell state. If meanwhile that also changes, then how we can compute? So that is some sort of freedom of choice that we have. So that is a fundamental difference between computing and the quantum physics or mechanics. Now this is introducing quantum computing in cryptography. You can see the first idea was proposed, though BB84 or the quantum key distribution, they were proposed somewhere around early 80s. But in 1960, Stephen Wisner, you can see his picture, has suggested some ideas in quantum information theory, where one such idea was quantum money. I'll be showing you the picture of quantum money, where it was used to actually prevent some sort of, say, bankruptcy or something like that, where some currency note like he discovered, and he just relied on the physics for that. Again, physics comes into picture with the quantum physics, where he said that okay, something can be cloned or copied, right? That is a forgery, can be done if it is some paper note or something. But instead of that, what if we can make some note where it will be 20 light traps, or say 20, say, holes are there, kind of. So that is a tiny device that can capture and store a single photon. And each photon can be in any of one of the four bases. Either it can be horizontal, say this thing, either it can be horizontal, or it can be vertical, or it can be 45 degree, or it can be 135 degrees. So in any of the directions it can actually horizontal, vertical. Likewise, it will be having possibilities. Okay. So we call it like this, either this base or plus minus base. This is called either this thing or this thing. This is the horizontal, vertical, and this is the plus minus bases. But in total, there can be four different bases. So the first light trap can give you four possibilities. The second light trap can give you four possibilities. Third, four. Likewise, how many possibilities can be there? How many total light traps are there? 20. So there are 20 such light traps or photons in easy words. And each can have four possibilities. So what can be the total possibility? Base to the power exponent, 4 to the power 20. If you want to write it in form of 2's, then it will be 2 to the power 40. So to forge one note, there are 2 to the power 40 possibilities, which is of course very difficult, at least in that era, 1960. Right? And what will happen if you try to maybe tweak one such light trap? That too you just change one basis, what will happen? It will not be exactly same. That means no two currency notes are exactly similar. And if you try to even do any forging where you will have to forge some quantum bit, it will distort your quantum state. So that means the original note cannot be copied or cannot be forged in any means. Okay. So, and how you can identify that between the original and the forged one? Each bill is identified with a traditional number and a database containing the polarization state. You will be having that dictionary with you. So if there is any such change in the polarization, you can actually immediately identify that there is a theft, there is a forgery in the system. But this seems to be too good to be implemented, and that is why, because it was so costly, this idea of like preventing the counterfeiting. This was so like difficult that it was actually, you can see here this thing. So how feasible quantum money is right now, not practically implementable with the current technology, as quantum states must be stored in some quantum memory. You have to store it, right? So retaining the quantum state in that form, because in the dictionary, whatever you put, actually you have to in reality also implement that. So that is why this idea, though it was a great idea, but it was a part of the futuristic idea. So till now we haven't implemented it because of quantum memories, they suffer from the decoherence. And even or not only that, if likewise if you put all the kind of thing on a small note, say likewise, so there will be some effects of this qubit and this qubit as well. So there are chances of interference because it will be very highly coupled, highly coupled qubits. So interference plus highly coupled qubits plus decoherence plus cost. So cost is primary. So cost plus interference plus this thing, all these things are making this particular thing really infeasible. But the idea was so good that it was the fundamental, again, fundamental core principle of the latter known, very well known algorithms like BB84 or these kind of QT protocols. So it was nearly, at that time, it was nearly $1 million per bit per note. You can imagine that much of cost is not really doable in real time. So this is also known as a quantum cache. And it was end of counterfeiting. So the idea was super, which was being proposed by Wisner. So this is how it looked something like this. Okay. And the polarized light and polarizations, you can see that whenever a light photon travels through the space, it will it will actually vibrate in a plane parallel to the direction of the photon it is traveling. So this is the unpolarized light, this is the polarized light, and this is the polarization vector. Depending on the vector, angle, and all, a few of the signals will be passed through and few will be blocked. Hmm. Okay. And these two are also very important point. If the filter and the photon have polarizations which differ by 90 degree, then the photon will not pass through the filter. And if it is like, that means if I have a horizontal one filter, and if I am sending a vertical, say, photon, then that will not pass through at all. But if the filter and the photon have polarization which differ by 45 degree, then the photon has 50% probability to be blocked or it has 50% probability to pass through. It depends. But the possibility will be increased. Right. So this is the famous BB84 protocol where it uses a set of four polarizers and two bases, horizontal, vertical, and diagonal. So you can see that these are a few examples of when it actually passes through and how it can be blocked, or how the filter and the like photon, they both have to say look like the same thing. So these are the two bases. This is the plus minus base and this is the horizontal vertical base. So horizontal vertical base QT-00, this is horizontal, and in the plus minus base, this is the plus, and this is this thing. Now this is nothing like fixed one. You can also pick like K0 will be vertical and K1 will be horizontal, or plus will be say plus 45 and minus will be 135. You can also take the reverse, but the thing is, whatever I will be taking, whenever we will have to choose that particular thing in communication channel, both of them have to actually agree with that. That is, the sender and receiver has to agree with the kind of the polarization angle and the like what you are trying to encode. Both of them have to be same. But the convention you can definitely change. But only thing is both have to follow the same convention. So initially the idea is something like okay, before talking about this thing, first I want to just talk a little about that what is QKD. If there is no slide. Okay. So what is QKD? So QKD is quantum key distribution. Now, of course, you can ask that why suddenly uh, instead of a quantum encryption algorithm, why we are directly jumping to the quantum key distribution? Well, the answer for that will be see, we have to consider a few of the practical things. And one participant in NIT Patna, he was one of the associate professors there. He actually was asked this question to me that why only we are sending and only we are focusing of quantum key distribution, why it is not like a quantum data distribution, because ultimately what is our target? Our target is to protect the message or the data. So if I only protect the key, will not my data will be like affected? You might be having this question. Okay, so the real answer behind this is, or I don't know whether how much real it is, but the most logical answer it is that see, quantum itself is so costly. So here sending something itself is so tricky. There are a lot of like decoherence. You need to incorporate repeater. A lot of such things are there. And data size, there is no restriction. You cannot really restrict the size of the data. So even if for the consider the block cipher where every data will be transferred in form of blocks. So there will not be one block. There will be multiple those many bit size blocks that I have to transfer. But if I employ quantum for editing, then that is little not so demanding. Why? Because of course that is not required. If you have to say you need to protect your house and you are going to office, then what you will be carrying? Your entire house with you, or just the key with you? So the most important is what key you are using, whether you're using a Godrej key or some very strict security principles, maybe some CCTV camera you are like you have deployed in your say neighboring positions. What you are actually deploying, that is very important. So every time we have to think about a real time solution rather than always a theoretically based one. Again, it cannot be like a quantum and it cannot be too good to be true. So definitely here also our target is to protect the key. So just we will be generating the QKD key or some of the keys, cryptographic key. Then our target is how we can simply distribute it between the sender and receiver every time we initiate a communication. Because every time whenever we are initiating a communication, we will be separately using one cryptographic key each. For all the rounds, it cannot be one, right? So that is why we have to protect our key first, or have to very securely distribute our key. If we can protect that, then the data will be uh, under no disturbance, has a lot more probability than directly protecting that bulks and bulks of data. On how we can transfer it, that much of a quantum communication channel and all the things is not yet developed. So that is why what we want is we rely on we generally use a mix of that. But right now what we want is how to securely generate a cryptographic key and how to transfer it or how to distribute it between sender and receiver. And here also, that is why we call it a quantum key distribution. So it's using a quantum channel, you need to distribute some key generated using QKD. Now again here, it's similar to the teleportation. Here also the concept is exactly same. There are a bit of set of predefined rule available for both sender and receiver, just like something was available to the for the Diffie-Hellman key exchangers as well, a part of root and a part of the like part of key that was available for the modulus that was available, and a private root was available, something like that. And depending on that, a shared key was generated. So here also the idea is same. Something will be shared. Alice and Bob both will be having some agreement on some few points that they both will be using same type of bases, and both of them will be doing certain computation, and both have principles to discard if it is not up to the mark as per their earlier set, say preconditions that they had said earlier, that how and when they will be accepting a key generated, and when and how they will be discarding or rejecting a key generated. So on that note, let us start the process. So it is also not like distributing the key, that is Alice will be generating the key and that key will travel, it is traveling through the communication channel and is reaching to Bob. This is not the case. Here also some information will be shared between Alice to Bob, something Bob will be receiving. Based on that, Bob will be understanding or discarding something that, and also Bob will understand that whether there is some intruder or man in the middle attack or not. Now, if there is a man in the middle attack, QKD principles are so well defined that it can be detected very easily. Once the attack that is detected, what Bob will do is both Alice and Bob will simply discard the key. They will not be using it anymore. So it is not that that key is very, very secure. Rather, the fundamental thing of QKD is if the key is somehow tampered or some sort of malicious attempts have been made on that key, then it will be very instantly detected by both the parties and they will simply discard that instance of communication and they will again reinitiate another one, a fresh one. And they will be keeping on doing it until another. In that sense, in that way, now they will be having the same key. Okay. So after that, Alice and Bob will be using this shared key in order to perform the further cryptographic steps. Okay. Let me again put a little pause. Let me ask if this is okay or not. Hidden variable means unknown or invisible particle. Yes, something that is that supports realism, but we might not be having detailed understanding of what are they. A lot of such fields, a lot of such other like macroscopic or nanoscopic particle, they might be having some influence on the quantum level, at the quantum level on the qubits as well. Why only? Okay, there is another question. Why only? Uh, that is the again that is the logic on which we want to do it, because if 00 is there, then I just do not want anything to happen. That is why I'm not doing anything. So this is simply I. That is the logic. Why you have to do that? See, of course, there are a lot of research ideas behind that. They must have tried a lot. After that, they have come up with the idea that okay, by employing these two gates and this order, what I want that will be accomplished depending on the requirement. There were certain questions. So, Dr. Pavani, right now, have you understood it? Because I explained the entire dense coding again after this. So, why on Hadamard on first qubit and all? Second qubit is 0, then possibilities are 0010. Yes. No, 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 sorry, sorry. So second qubit is 0. Second qubit is 0. Only this information is giving me what? See, second qubit is 0. In that table, if you remember, the second qubit is 0, and we are then measuring the first on the first qubit, which can be either 0 plus 1 or 0 minus 1 by root 2, right? And on measuring that, I can get 0 or 1. So possibilities are 0010 whenever we are doing the Hadamard on the first qubit. But if that case 1, 2, 3, 4 you consider, one is what I have sent. Okay, I got the confusion. One is what I have sent, another one is what I am receiving. Or if Alice has sent 00 or 11, then only the second qubit will be 0. Bob has seen that thing. Now, if the second qubit is 0, fixing on that one, possibilities can be 00 and 10. That is the thing. Okay, any doubt again? Any specific doubt anyone has? I'm just waiting. If you're having any doubt, you can ask. Or if it is clear also, then let me know. I will be talking about BB84. That is what I will just start. There is no doubt earlier. I just have talked about what QKD is and why we only need to protect the key. Now we will be talking about the one of the QKD protocols, which is BB84. Okay. So another few seconds, or can I directly start with BB84? See, I think no teleportation. Maybe some nested teleportation. I don't have much of the knowledge about the like optics. What how the developments are happening in that space. But if I'm not wrong, uh, it's not much developed yet. Or maybe we are just decomposing it and just maybe only fixing for that thing only, not more than that. I'm not exactly sure about how they are supporting it. For so I will not make much comment on that. But when last I have seen, uh, I just have some knowledge about the distance part. But maybe they use some sort of repeater or something. But together simultaneously, there shouldn't be like multiple qubits that can be sent in practice at least. I think so. I have not ever heard that multiple such things can be sent together. So that is what I'm telling. Maybe there are some advanced versions. I have to also check them. Sure, sure. Thank you, sir. One thing I can tell that there are a few like companies that are working on this space, which you can see, which is ID Quantic. See what the challenge is. Even in PwC, I set up a meeting with them, but the persons who talk about they do not disclose anything. They just send a big manual for QRNG as well. So they just give you that application level thing. We a lot many times ask them about the POC, so they just give us that kind of supporting document that, okay, see, we have these many certifications. So from that, all the detailed technical specifications they never talk about. They just specify the hardware level that, okay, so this has a speed of this, so this has a the thing of that. So what industries exactly they're following, that is why it's very difficult right now to judge or to properly test whether something what they're committing, that it is quantum, how much quantum it is. So I personally has talked with ID Quantic members. They just have that, okay, if you have this type of application, you can get this device from us. If you have some more, you can have this device from us. But and there are research definitely going on. But what industries they're actually adopting, they're not disclosing it. Maybe for like competitions and all, monopoly or something. So business angles are there. So which we technical persons will not be understanding much more. And so it's still, I don't think that they have really adopted it. I don't think so. And one Chinese company is there, they actually have incorporated the QKD with 180 kilometer successfully, and more than that. And that was also like in between two data centers of them. So that's kind of an in-house setup that they had. So, and after that, commercially though they are giving, I don't think it's same as Bitcoin. Bitcoin, does it really use some quanta like photon bits in Bitcoin? The itself, the like hardware is different, technology is different. Quantum money is never implemented till date. It is it's basically you can assume as a big quantum, say, machine, one quantum machine for one particular bill or one note, something like that. So I do not know. Bitcoin they use really photon. I don't have much knowledge of that. I don't think so. But here, all the they just use light traps, so nothing like that. So or like a photons they are moving, and each of them are holding one unique combination, one unique configuration, which actually maps to one single money. So for that, we also need to mass scale production like China. We have to keep on generating the photon devices and have to, and that too at a very cheap level, and have to practically implement the quantum money. It should be like that. This is all what my understanding is. It should be like, yes, yes, yes. And here the principles also are very different. I think the basic blockchain here, tampering is not exactly the tampering of the that particular thing, like the photon bits. So here the consensus is there, and some chain of like verifications are there. So if you break one, it will be broken. So it's kind of an hashing technique, I guess, but it's not exactly same as the like quantum cryptography at least. Yes. So what I was talking is, Toshiba is a company which is working on QKD. QNew Labs also we can check, which is an Indian company. They are also working on that space. But still, I think their products are a bit more aligned towards some hybrid solution that they're trying to explore, and the QRNG device. That is what they are currently offering. Only I guess Toshiba and ID Quantic they are into the solely QKD space. But you can try exploring what they are offering, but they are offering are not really very clear. And what are the technologies that they use, definitely that is in like closed, that is not disclosed. Okay, they will industry will never be very transparent to you that yes, these are the things that they are doing. There will always be something very clumsy, something very tricky, something is there but still not there kind of thing. And with all industries, I'm just telling, this has to be true, the core ones as well as the consulting ones as well as whatever space you look into. Okay, I think now we can start BB84, right? We can start with the rest of the QKD. Is it okay now? We can start with this. Okay, so I'm just assuming that I can start now. Yes. So the BB84 protocol, sorry, so the BB84 protocol is by Bennett and Brassard. This is the spelling, I guess. I guess in 1984. It's not written. Yeah, I know that in 1984, kind of. This was actually invented by them. And this was a research paper where they proposed this QKT protocol, BB84 protocol, because it was developed in 1984 by Bennett and Russell. But when they submitted it, IEEE actually rejected it. And it took IEEE to accept the paper after, I guess, 12 or 15 years. So, you can imagine that. And right now, it's a milestone idea. And this was inspired by the concept of the quantum money. So here, Alice will toss a coin first. Okay. Now, whenever we are tossing a coin, it can have either a head or a tail. So depending on that, Alice will generate a random sequence of 0 and 1. Now, say if the outcome is head, then she will use a horizontal vertical basis. Now, this can be a plus minus basis as well, but this is what their assumption is. Again, I've told you, you have to follow the same assumption for both the Alice and Bob. Say, for example, if head, then Alice will be choosing horizontal vertical basis. Otherwise, she will be choosing the diagonal or the plus minus basis. But if Alice chooses a horizontal vertical basis, then the condition is Bob will also have to choose the horizontal vertical basis for his part of measurement as well. Okay. And here each bit is encoded as 0 or 1. Okay. And Bob receives each bit but does not know how to decode it. So he also will toss a coin. Let us see how it works. Say Alice wants to send the bit stream this. This is not the key, this is just the bit stream. The key will be a subset of the bit stream, or say multiple bit streams also one key can be generated. Okay. So say Alice wants to send the bit stream 1001 1000 to Bob. So 1001 1000 is there. Alice will toss a coin. So Alice can get either head, tail, tail, head, tail, head, head, tail, likewise. Of course, this is independent and is not dependent on what initially Alice has. Okay. And these are all the bases chosen by Alice. So if it is head, he will be choosing a plus minus. If it is a head, it will be choosing a plus minus. If it is head, it will be choosing plus minus. If it is head, it will be choosing plus minus. And if it is a tail, then Alice will be choosing a diagonal. Here also it's a tail, so diagonal, tail, so diagonal, and tail, so diagonal. Now it will be sent. The arrow is bit little up. It will be sent to through the communication channel to Bob. Now, whenever Bob will receive it, first Bob will also use, whenever it will be like this, then Bob will also toss a coin. Say this is the outcome of Bob's toss. Head, head, tail, tail, head, tail, kind of. Then Bob will choose his part of his part of basis as well. How it will choose? Same logic. If it is getting a head, it will be a it will be a horizontal vertical head, head, and head. Otherwise, it will be tail, tail, like the diagonal ones. Okay. Now, what are the bit that will be received by Bob is, say, when both the chosen bases are plus and plus, that is a horizontal vertical, whatever was there to Alice, that will be successfully transferred to Bob. So Bob will be receiving a 1. Similarly, just check for the same basis, where the basis is same. Yes, here also it is same. Not same. Yes, here it is same. and here also it is same. That in remaining cases, their bases will not match, right? So in these cases, definite these are the four definite cases 1 0 0 0, and the remaining case is one is horizontal like this thing, diagonal this is horizontal vertical likewise, that is their basis different. Now say this is the thing, this is something that Bob received. Now say, so this is the calculation by Bob. Okay. Now say Bob gets this thing 1 1 0 0 1 0 0 0, and original bit stream was 1001 1000. So out of this you can imagine that this is supposed to be correct, and yes correct, this is also definite correct, definite correct, and definite correct. But out of the four cases 1 2 3 and 4, somehow though their bases do not match in all the four cases, in two cases exactly the values are differing. It is 1, it is 0, this is 0, this is 1. And in these two remaining cases, if you see, though their bases are differing, they are getting the same value. So out of the 8, 4 are definite case, and remaining 4, 2 are definite mismatch and 2 are probabilistic match or probabilistically correct, right? Now, say assuming large number of bits are being sent and Alice is doing a random experiment of tossing a coin. And half of the time Alice uses a horizontal vertical and half of the time Alice uses a plus minus basis. That is it is more or less uniform. And assuming there is no eavesdropper or no attacker in the scenario. Hence half of the time Bob's basis will be same as Alice's basis. Some bit received in 50% of the time as sent. In another 50% case, where Bob's basis and Alice's basis they will mismatch. Then also probabilistically out of those 50%, again for remain a part of the half cases, that is again for 50% cases, they will agree. That is their outcome will match. So that is 75% of the cases it will match. So the agreement between bits sent by Alice and bits received by Bob is as much as 75%. This is the maximum agreement. So though Alice and Bob will agree 75% of the time, but only for 50% of the time they have used the same basis. These are all statements, like this is how the algorithm has been developed. So now Alice will uses a classical channel to announce that okay, I have these I have used these bases. See now this till this part we have got it in the image itself. So after this thing, after Bob is done with the receival, after a certain time, as it should be, for the successful transmission to take place, what Alice will be doing is Alice will be in publicly announce that what are all the bases that he has chosen. This information now Alice will be publicly announced through some public channel which is available to all. That is, Alice will not be telling that whether 1001 1000 these bit stream Alice will not be announcing. Only the basis chosen by Alice will be announced. There are uses a say vertical, horizontal vertical, HV, D, HV, something like that will be publicly announced by Alice through the classical channel. Okay. Now, after the bit transmission, as I said, Alice will announce her chosen basis in sequence. That is HV, D, D, HV, D, HV, D. This particular combination will be sent in public, not the bits that she has sent. After this, though 75% of the cases, they agree somehow probabilistically, like 50% was correct, 50% out of 50%, 25% is probabilistically correct. Though that is the case, but Bob will be removing all those bits where Alice's basis and his chosen basis do not agree. So to maintain the uniformity, agree only for those 50% of the time where both the bases are same. And for the remaining 50% of the time, he will be simply discarding or disregarding also will work, discarding the probabilistically correct outcomes. Okay. Now all these things are happening when on what condition that there is no eavesdropper in between. There is no attacker. It's a simple ideal scenario where there is no hacker, no attacker. No man in the middle attack is ever possible. Alice and Bob will be there, and after that, so 50% of the time they will be agreeing, otherwise they will be not be agreeing. Right? And how it will Bob will discard depending on whenever Alice will be announcing his chosen her chosen basis through the public channel, Bob will be discarding based on that. So maybe few bits there is a match, still Bob will be discarded. But the real scenario is so of course the no cloning theorem and all that will be supported. Right? There will be no cloning theorem. So a copying device can only clone orthogonal states. Since an arbitrary superposition of states are not orthogonal, we have seen only the identical and orthogonal states can be cloned. So that means here also they cannot clone any of the data. And secondly, this is only on that assumption that there is no such intrusion of Eve in between. But if there is some intrusion, then what to do? That is not yet defined here. And the next one is, what if Eve has a possibility to tap in what Alice sends and keep that and make an identical copy? So what will happen in that particular case? Okay, so now we will look into that thing, or we'll try to analyze that what will happen if we have some intrusion or possibility of intrusion in between. Okay, let me again ask the simple BB84, is it done? Then we will actually look into this. Then we will look into the last case, which is the this particular thing. What will happen in the intrusion of or after the interception of Eve? Is it done? Just give a quick thumbs up. Is it done? Because on the same assumption, we will talk about the actual QKT-BB84 on application of Eve. I think it is done. Is it done? Have you got the basis and all? Please let me know. Okay, thank you. So the similar logic I will be just expanding. So let me put a few slides here. I don't have much time left. Anyway. Yes. So now you can imagine, say, a little fast, say Alice has 1001, 1000. Basis chosen is this thing. Or let me put a plus here. Say plus into plus into then plus and then diagonal. And Bob was somewhere. Bob's bases were plus. Here also plus. Here it's a diagonal. Here also diagonal. Now you should be knowing that how all these things are happening. Now say in between somewhere Eve is there or the intruder is there. So it is the intruder. So this will be plus, say, and Eve also does the same thing. It's a man in the middle, right? So Eve will try to actually mask herself in a way that he is the or she is the intended receiver. So she will be following exactly the same steps as Bob follows. Exactly the similar way. Toss a coin, depending on some basis, will be chosen. So somewhere in the middle of Alice and Bob, Eve should be sitting. So say for example, this is something that Eve is choosing. So what it will pass like here it will be 1, then here it is a definite 0, and here it is 1, then here it is 0, and like nothing like that. And here it will be now Bob, whenever Bob will be getting something because somewhere in the middle Eve is doing something. So when it will actually not be blocked by the polarization filter of Eve, then only it will be successfully received by Bob. And when it will be not be blocked, when Bob will be receiving what Alice is sending to him, when the Eve and the Bob as well as the Alice's, all of their polarization filters are same. So whenever these three are same, it will be 1. Now in this particular case it will be 0, and nowhere else all of their bases are same, right? Because in these two cases only all of them are same. Okay, so therefore we can understand one thing, that if Eve is not present, then probability vertical vertical or say diagonal diagonal, this is horizontal, can be, it can be as well, it is 1 by 4, or the polarization can be, sorry, this is the polarization chances. Therefore the probability of getting right is half, that is 50% of the time. We have seen that it's 50%. But in presence of Eve, this thing, that polarization of all these things will be same, that is 1 by 8, right? Therefore total probability will be 25% the instead of the 50% of the probability. And why this is the case? Because Eve chose right basis, she chooses, if that is the intruder can choose the right basis, say half, and Bob chooses the right basis, and it is same as Alice, as per Alice, and not blocked by Eve or say Eve's filter. It's basically this probability times half, which is 1 by 4, that is 25%. So that is why Alice will choose for a safer transmission to take place. Alice will choose 4 into n. Why? Because out of n, if n is being sent, then n by 4 are the successful bits being transferred. So in order to successfully transfer all n, definitely Alice chooses all the 4n bits. So that is 4 into n by 4, that is after cancelling out, and after though if it's present, after all those things, it will be a little as it should be, plus delta. Delta are just for some safety bits kind of thing, some additional parity, additional number of these many number of bits. encodes them randomly, and send to Bob. This is the first thing. So the second one, you know that Bob measures them using random base. Random basis. Then public announcement by Alice. Public announcement by Alice, but not actual bits of basis, right? Not bits. Then next is, this is I guess step 3, this is step 2. Let me write step 1, this one as now. Next is, in all likelihood, at least in 2n cases, their bases will agree, right? Okay. So likelihood in best case is at least 2n, then an extra delta is to compensate for the possibility of actual agreement. We rely a lot of on the probability here. Agreement can be maybe less than 50%. Then Bob discarding all unmatched basis outputs, right? Now Alice now chooses a random n bits. This is very important. That is, Alice now chooses a random n bits. They're not necessarily consecutive. Say fourth bit, seventh, 13th, and say 17th bit, and will announce it, publicly announces these actual bits and their locations. The fourth bit is 0, likewise say fourth is 0, seventh is say 1, 13th is say 1, and 17th is 0. That is actual bits as well as their locations in a public channel or through public channel to Bob. And this is all after Bob discarding. So till the discard phase is over, now you just imagine how the keys are being generated. Just pardon me with 5 more minutes. It will be done. So after Bob has discarded and got something, now there is certain sort of verification or further further tuning, security tuning. Okay, so Alice will now publicly announce a few of the bits. They may not be consecutive, that can be any random bits, as I just mentioned, 4, 7, 13th, and 17th, in a public channel to Bob. And now Bob, what is this step? Step 6. So 7 is Bob checks all. Okay. If discrepancy, that is a gap between 6th, 7th, 11th, 13th, and or say 17th, if the discrepancy is very large, say all 4 bits are different, then Bob, what will do? Bob will simply disengage and initiate a complete new key exchange or communication. Key exchange communication. But if say discrepancy, say delta, is little less. Okay. Then again some n bits will be sent until the range is acceptable. And 9 is condition applied that it is if acceptable, then that part of n bits or total n bits. Remember, we have sent 4n plus delta bits. N bits will be my OTP, one-time password, or quantum key. Okay, and in simple words, this is how quantum thus we achieved. Thus, quantum key will be distributed to Bob, and this is QKD. Okay, and this is the end of our quantum communication. And of course, you can understand that intrusion detection is really very easy here, because presence of Eve in classical cannot be detected. So in quantum, we can actually detect the presence of Eve whenever there are like a huge number of bits discarding, or their bases are not matching as it should be whenever Alice publicly announcing something. So very easily Alice and Bob both will be understanding that, okay, that particular communication is a false one, or it is very much of an under attack, and we have to again establish a new communication setup. Okay. So one more thing is here that I want to end with is QKD is also not fail proof. It is only intrusion detection enabled. So the man in the middle attack in QKD is not possible. Intrusion, definitely if someone tries to do it in classical, they can also try to do it quantum. But the detection was not possible in classical, which we can detect in, on the contrary, in quantum. Okay. And here is the end of my topic, quantum communication with you and cryptography. Right. So anyone, any doubt, anything you have? Have you all understood the BB84 protocol? First, something is being sent, then we are applying a few further steps just to share or establish the session, or establish the session key. Okay. Thank you.
Thank you so much, ma'am. It was a very insightful session, and of course, with a lot of write-ups as well as visualizations. So thank you so much once again. Uh, Participants, if you have any questions, please post right now. Um, Although ma'am has answered almost all the questions during the session itself, so most likely you won't be having any questions right now. Okay, ma'am. So we can conclude. Thank you so much once again.
So
Sir, good
much.
evening. Thank you very much,
Yes, sir.
madam.
Yes, sir. Yes, sir.
A really wonderful session, wonderful presentation. Thank you so much. Even non-technical faculty also can understand your talk. Sir, is there any quiz today or tomorrow?
No. We will have one more
No.
quiz, but we'll soon announce its date and time. So that will be the last quiz number 3. Okay.
Okay, sir. Okay.
Okay. Well,
So the
mostly
next
after
session will be
3
on Monday only.
Yes, next session will be on Monday.
Thank you, sir.
Thank you. Thank you.
Thank you, everyone. Thank you, participants.
Thank you.
And if you want to connect with me, if you want to, you can connect on LinkedIn. That is the most effective way. I regularly almost check it. So we can get in touch or connect there.